Hello. So today what we're going to be talking about is something called the first derivative test. So last time we talked about how to find where functions are increasing and decreasing using the first derivative, and now we're going to learn a way to use that information to find where extremas are. So before we were trying to figure out on just closed intervals where our minimums and maximums were, and we could do that because we could just plug into the function and actually find the y values to show which ones were the biggest and the smallest. But now say we're looking at a function over the whole domain of the function, so usually the whole real number line. And we want to know where all of the relative minimums and maximums are. So in other words, where are those turning points of the function? We can actually use the information we get from an increasing and decreasing problem to do that. So we have something that's called the first derivative test. So if c is a critical value for f of x, so in other words, if c is a place where the derivative is either 0 or undefined, if on our sign chart, if you remember the sign chart from last time, if our derivative goes from a negative sign to a positive sign over c, then we have what's called a relative minimum, which makes sense if you think about what negative and positive derivatives are. So a minimum looks something like this. A minimum is at the bottom of a u. And here, if we draw some tangent lines in, we have negative derivatives over here because the slope is negative, but we'll have positive derivatives over here. So that's why the minimum is going to occur there. Now, if the opposite happens, if the derivative goes from positive to negative at c on your sign chart, it's a relative maximum. And it's just the opposite of the picture above. So a minimum happens somewhere like this at the top of a u or top of a parabola looking thing. If we draw some tangent lines again, over here on the left we have positive slopes or positive derivatives, and over here we're going to have negative slopes or negative derivatives. So those are two nice little pictures that you could easily draw for yourself if you ever forget what going from negative to positive means or positive to negative. I know I usually do that on tests just to remind myself so I don't label something incorrectly. And we have the third case in the first derivative test where if you don't change signs at c, so if you either go from positive to staying positive or negative to staying negative for your derivatives over c, then c is neither a relative minimum nor maximum. And that's going to happen for something that kind of looks like the cubic function here. So something that looks like that, down here in the middle where your function flattens out, you will get a horizontal tangent line, but it's not a minimum or a maximum because it's not a turning point of the function. So let's do some examples now. Or first, let's draw some pictures. So the pictures that I just drew kind of illustrate that, but say we have a function that doesn't look like u's. Say we have something that looks like this. So now let's just draw in some tangent lines and pick out the points that we think are going to be the extremas. So the extremas are going to happen at the tops of these turning points. So we definitely have two here. And if we draw on our tangent lines here, all of these have positive slopes. But if we draw some down over here, these all have negative slopes. So since this is going from positive to negative, and we can see visually that it's a maximum, this is going to be called a relative max, or relative maximum if you want to write out the whole thing. And then if we continue drawing our tangent lines here, we see that over here at the second point, we have negative derivatives going into positive derivatives, so it's again a relative minimum. Which it's almost the same as the pictures we just drew, but this is if seeing it on one function altogether. And so that's how you could always see a relative max and min. We know that a maximum happens at the top of something and the minimum at the bottom of something, but knowing how it relates back to the derivatives is a very important concept. So let's do some examples and find them. So let's pull some trig in here. Let's find the relative extrema of f of x equals 1/2 x minus the sine of x on the interval from 0 to 2 pi. So from all the homework you've done and what you've seen in class, you probably realize now that whenever trig gets involved, we usually just look at it over an interval since trig functions are periodic and repeat themselves. So there's an infinite number of solutions usually. So we learned from the first derivative test that we want to look at how the signs of the derivative change, which means that we need to find the critical values of our first derivative. So we should probably find what our first derivative is. So f prime of x is going to be equal to 1/2 minus the cosine of x. Now the cosine of x is always defined, so we don't have to worry about the derivative ever being undefined. So we're just going to set it equal to 0 and solve for x. So we have 0 is equal to 1/2 minus the cosine. If we move our cosine over to the other side, we get that cosine of x equals 1/2. And so now we just have to use our knowledge of the unit circle to figure out where the cosine of x equals 1/2 in 0 to 2 pi. So the cosine of x is going to equal 1/2 in the first quadrant because all of our trig functions are positive there. It's going to happen at pi over 3. And then it's going to happen again in the fourth quadrant of the unit circle because our x-coordinates are positive in the fourth quadrant, which means that cosine is positive. So that's going to happen down at 5 pi over 3. And so now all we want to do now is set up a sign chart. So let's label our f prime, x's, put our critical values on there. So we have pi over 3 and 5 pi over 3. Now since this is trig, it gets a little harder to plug in, but not too much harder. So let's pick 3 test values. Pi over 3, we could always plug in, pi over 6. We could plug in pi for the interval in between, because pi is definitely in between those two. And then we could plug in, 5 pi over 3, we could do 11 pi over 6. See what happens. Okay, so now let's plug those into our derivative and see what the signs are. So f prime of pi over 6 is the same thing as 1/2 minus the cosine of pi over 6, which is going to be equal to 1/2 minus the cosine of pi over 6 is positive, and it's going to be equal to root 3 over 2. Now, root 3 over 2 is a bigger number than 1/2, so this answer is all around going to be negative. So we don't necessarily always have to find what the exact value of the derivative is. If you can see if it's going to be positive or negative, you just need to know the sign. That's all that matters for our sign chart anyway. So now let's do the same thing for pi. So at pi, we're going to get 1/2 minus the cosine of pi, which is equal to 1/2. And the cosine of pi is going to be -1, so plus 1, which is going to be a positive number. We don't really care what that number is, so we'll just put our positive sign on there. And then we'll do f prime of 11 pi over 6. Okay, so 11 pi over 6 is going to be 1/2 minus the cosine of 11 pi over 6. And the cosine of 11 pi over 6 is also going to be root 3 over 2. And it's a positive root 3 over 2 because it's in the fourth quadrant, so we know our cosine values are positive. So again, we're going to get a, whoops, not a positive. Since root 3 over 2 is bigger than 1/2, we're going to get a negative number here, so we'll put a negative sign up here on our sign charts. Okay, so now we have some changes going on. So now we're going to use our first derivative test to determine if pi over 3 and 5 pi over 3 are relative minimums or maximums. So what I like to do sometimes is to draw those pictures. So at pi over 3, I'm going from a negative to a positive, which means I have a picture that looks like this. Well, that's going to match up to this being a minimum. And then at 5 pi over 3, I have a positive sign to a negative sign, so something that looks like this. So that's going to be a maximum. So now it's really easy for me to say that, okay, f of x has a relative minimum at x equaling pi over 3 and a relative maximum at x equaling 5 pi over 3. And that's all it is. So all you want to do again is you want to find your derivative, find all your critical values by setting it equal to 0 and solving and looking for where it's undefined, and then doing your sign chart and seeing how the signs of your derivatives change. So let's do one more. So let's do it for f of x equaling x to the fourth plus 1 over x squared. Now that looks really complicated. You're probably thinking, oh man, we got to use quotient rule, that's so much work. We don't actually have to use quotient rule. Let's actually simplify our function first. So if we split that fraction up to being x to the fourth over x squared plus 1 over x squared, we can simplify this to be, well, x to the fourth over x squared is just x squared plus x to the negative 2 rewriting that fraction so that our x's come out of the denominator. So now it's a lot easier for us to find our first derivative. So let's go ahead and do that. So the derivative of x squared is just 2x. The derivative of x to the negative 2 is negative 2x to the negative 3, which is equal to 2x minus 2 over x cubed. Okay, so now we have to look for our critical values. So we notice here that if we plug 0 into our derivative, so f prime of 0, that's going to be undefined because of this term here in the back. So we know that x can't equal 0, so this is a critical value, and we're going to have to look at that. So this is the first time we've actually had a critical value that came from a function's derivative being undefined. So now let's set that 2x minus 2 over x cubed equal to 0 and solve. Okay, well let's first add 2 over x cubed to both sides. So we get 2 over x cubed equals 2x. If we multiply everything by x cubed to get rid of our fractions, we get that 2 is equal to 2x to the fourth, which if we divide everything by 2, we get 1 is equal to x to the fourth. Moving that 1 back over, we get 1 is equal to x to the fourth minus 1. Then all we have to do is factor. So that's going to factor down into x squared plus 1 times x squared minus 1, or x squared plus 1 times x plus 1 times x minus 1. So now we just have to set each term equal to 0 and solve that. So x squared plus 1, 0 equals x plus 1, and 0 equals x minus 1. Now, x squared plus 1, that has no solutions because if we moved it over, we would have negative 1 is equal to x squared, which is never true because squares are always positive, so there's no solutions there. And then these two other terms are really easy to solve because they're linear, so we get x is equal to negative 1 and x is equal to positive 1. So now we just have to set up our sign chart and solve. So for our sign chart, we're actually going to have three numbers to test. We're going to have negative 1, 0, and positive 1 for our derivative. So at negative 1 and positive 1, we had a derivative of 0, and at 0, we had an undefined derivative. So for those, I like to put an x above them, just to remind myself that those were undefined. So now let's pick some test values. We're going to need 4 here, so let's do f of negative 2, negative 1/2, positive 1/2, and positive 2. Okay, so for f prime of negative 2, we're going to get 2 times negative 2 minus 2 over negative 2 cubed, which is equal to negative 4 minus 2 over negative 8, so plus 2 over 8, which is 1/4, which is going to be a negative number since 1/4 is less than negative 4. Do the same thing for negative 1/2. 2 times negative 1/2 minus 2 over negative 1/2 cubed. Well, that's going to be equal to negative 1 plus, and then 2 over negative 1/8. So the plus sign comes from the negative and the negative 1/8. So 2 over positive 1/8 is going to be 2 times 8, or 16, which is positive 15. So that's definitely positive. Let's figure it out for 1/2 now. So we're going to get 2 times 1/2 minus 2 over 1/2 cubed, which is equal to 1 minus 2 over 1/8, which is 1 minus 16, which is negative 15. So we'll have a negative sign here. And then we'll actually have one more to do, so f prime of 2 rather. We already know what f prime of 1 is. So that's going to be 2 times 2 minus 2 over 2 cubed. So that's going to give us 4 minus 1/4, which is going to be a positive number. So now all we have to do is write our answer up. So we can say that looking at um, our sign changes, since we're going from negative to positive here, we're going to have a minimum. And then looking carefully at that undefined value at 0, if we look back at our original function, 0 is undefined for the whole domain, so x can't equal 0. 0 is actually a vertical asymptote there. So since it's an asymptote, even though we have a sign change going on here, the positive to negative makes it look like it would be a maximum, but f of 0 doesn't exist. It's an asymptote there. We have a vertical asymptote at x equaling 0, so we actually don't have anything. So maybe we'll label it as a vertical asymptote. And then we, again, go from negative to positive, so we're going to have another relative minimum at 1. So now our final answer can say f of x has relative minimum at x equaling -1 and +1, and a vertical asymptote at x equaling 0. So you always have to be careful at those undefined derivative terms by looking back to your original function and saying, is my function even defined for that number? So that's a slightly harder one. I hope all of this was very helpful to you. Thank you so much for watching. Have a great rest of your day.